Okay, so you guys took a look at Newton's second law into the lab where you had to measure the forces involved and the acceleration involved with the cart. Now, hopefully, you were able to work through that and you came to the conclusion that force is equal to mass times acceleration, and that's net force. So it's not just an individual force that acts on it, it's the sum of all the forces results in an acceleration. Now, this law actually makes a lot of sense because remember, inertia, from Newton's first law, is the tendency of an object to resist a change in motion. That is a tendency to resist acceleration, if you like. Okay, so in this equation we say mass, which is inertia, and acceleration are related by force, right? The bigger the force, the more acceleration we're going to get for a given mass. Okay. Now, it is important when you're using this equation for Newton's second law that you make sure your units match. Okay, and that's because by definition, 1 Newton is the amount of force required to accelerate 1 kilogram of mass at a rate of 1 meter per second per second. Okay, so if this is my box sitting here and it's got a mass of 1 kilogram and I want it to accelerate this way at 1 meter per second, then I have to exert a force of 1 Newton. Okay, so when you're measuring masses, they have to be measured in kilograms to use this law. The acceleration has to be measured in meters per second or meters per second squared to use this law. If you're given a mass in grams, then you need to convert it to kilograms. Okay, generally accelerations are given in meters per second, but pay attention to that. Okay, now once you've got the equation, you know how to use it, then it's just a matter of using the tools you already have. Okay, so an example problem. Space shuttle astronauts experience accelerations of about 35 meters per second during takeoff. Okay, so an acceleration of 35 meters per second squared. Okay, what force does a 75 kilogram astronaut experience? Okay, we're looking for a force, unknown. Okay, during an acceleration of this magnitude. Okay, and we were told his mass 75 kilograms. Now, we've got this astronaut sitting here. Here he is. Here's my astronaut. 75 kilograms. He's going to accelerate at 35 meters per second. We want to know, and I drew this wrong. I should not have drawn the acceleration arrow actually on the object. Okay, he's going to accelerate at 35 meters per second. Okay, we want to know how big the force is that causes that acceleration. So we go to Newton's second law. The only force, since this is his total acceleration, the only force we have to worry about is that one. So we can say net force equals mass times acceleration. And so this equals 75 times 35. Okay, I get 2,625 newtons. Okay, and that would be in the same direction of the acceleration, but it says it doesn't actually give us a direction. So 2625 newtons. Okay, another example problem. Okay, this one we're going to go ahead and we're going to pull back into some kinematics too. Suppose you pull a 20 kilogram wagon. Okay, so I like my picture. Here's a wagon. Okay, this is 20. Okay, and it's got wheels and it's got a handle. Okay, it starts at rest and has a velocity of 0.55 meters per second after you've pulled it 1.55 meters. Wow, I just got a lot of information. It starts at rest, so an initial velocity of 0 meters per second, and has a final velocity, or v, of 0.55 meters per second after I've pulled it 1.55 meters. I just got a change in position, 1.55 meters. What net force, unknown, do I have to apply to the wagon to get this to happen? Okay, and so I'm going to put one more thing up here, mass 20 kilograms. Alright, well I only have one equation involving force. Net force equals mass times acceleration. And I know the mass, but I don't know the acceleration, so in order to calculate net force, I'm going to need an acceleration. Now you remember from your kinematic equations that there are several equations that involve acceleration. I think the easiest one to use on this one would be the third one, because the third kinematic equation says final velocity squared equals initial velocity squared plus twice the acceleration times the change in position. And I know almost all of this information. I do not know the acceleration. Okay, so we're going to go ahead and use this equation. So final velocity 0.55 squared equals initial velocity 0 squared plus 2 times the acceleration, don't know, times the change in position, 1.55 meters. Okay, so we're going to go ahead and do a little bit of simplification here. If we take 0.55 and we square it, we get 0.3025 equals 2 times 1.55 is 3.1 A. So if we take 0.3025 and divide by 3.1, we get 0.0975. So divide by 3.1, divide by 3.1, and we get 0.09, I'm going to go ahead and call it 8 meters. Oh, that's our acceleration, meters per second. Okay. Now this is not our answer. Okay. That is just the acceleration. So I'm going to go ahead and I'm going to add that little bit of information over here. 0.98 meters per second. But now I can go ahead and use this to solve for that. Okay, so we're back up to our original equation. So net force equals mass times acceleration. So this is 20 times 0.098. Okay, and we get 1.96 newtons.